Hi, everyone. So today we're going over the method 2 video for finding work. This one we're going to talk about the scalar product. It's called the scalar product because you take the scalar of two vectors and multiply them. But you do have to take in their direction into consideration. So we'll talk about that. So in the picture that you can see on your screen, is the scalar product the area of the triangle? So we've talked about work being the area under a graph, right? But here, if we look at these two vectors, right, we've got vector A, and then we want to take B cosine theta because that is the component of the B vector that is in the same direction as A, right? You've got to look at the vectors relative to some direction, like we do with FD cosine theta, right? You look at the direction and what component of the force goes in the same direction as the displacement. So here we've got some vector B. The component for that would be B cosine theta, but that theta is specific. Okay, that theta is the angle between A and B. This is a special theta. That is the angle between A and B. Okay. That can't be any other theta when you're dealing with the scalar product. Okay, so if we take A times A dot B here, okay, this is the that's the notation for the scalar product. If you take A, B cosine theta, does that give you the area of the triangle? No, it doesn't. Okay, that is not going to be the area of the triangle. This is something entirely different. Okay, so number 2 asks, what is another name for the scalar product? So this is commonly called the dot product. The dot product is known because of its notation here. That is not just some tiny dot to mean multiplication. That should be a bigger, bolder dot to notate that this is specifically two vectors being combined using the scalar or the dot product. Now, do the units of A and B have to be the same? No, they don't. For example, work, right? If we use work as an example, let's say, let's fix this. Work, okay? That is force dot displacement. Now, that is newtons dot meters, and you get a newton meter, or that can also be called a joule. Okay? So no, they don't have to be the same. Another example is power. If you take force and use the dot product with velocity, you would get power. So this would become newtons dot meter per second, which can be called a watt. A watt is a newton meter per second. So it doesn't have to have the same units. This isn't like vector addition, right? Vector addition and vector subtraction, they have to have the same units, right? You can't add meters to newtons. That doesn't mean anything. But you can multiply meters and newtons. That does have meaning. All right, now, so that's 1, 2, and 3. Let's talk about number 4, right? So what is A dot B when the vectors are parallel? Okay, that is when theta equals 0. So if we look at A dot B, okay, that's when we take absolute value of A, absolute value of B times cosine theta. But if theta is 0, because they are parallel, cosine of 0 is 1. So that just equals AB. Okay. Now, if they are perpendicular, right? That was parallel. Let's say we've got perpendicular A dot B. Then you take A, B, cosine 90 degrees this time. That would give you a big fat 0, right? So very similar to what we talked about with FD cosine theta. If they are parallel, you've got both vectors being multiplied entirely. If they are perpendicular, it cancels out. They don't actually affect one another. So this works very well for work, right? It's obeying all of the same rules that we just had. Now, let's talk about a unit vector. And we've talked about them a little bit before. A unit vector is essentially it has a value of 1, and it is in one specific direction along a specific axis, right? So I just has a value of 1 in the x-axis direction, right? Same for j and k for the y and z axis. Now, if we take I dot I, right? I dot I, those are parallel, right? They are both in the x-axis, so you get I squared, which gives you 1, right? Same for j dot j, right? Those would be parallel, so you've got j squared, which equals 1, right? You've got, when you take 1 in the x times 1 in the x, you're just going to get 1. Then you have k dot k. That would give you k squared, which again is just 1. So this seems pretty easy, right? But you get your full value, right? I dot I is going to give you 1. Because I is in the x-axis, it's parallel to everything else in the x-axis. Now, what if we change this up? Let's say for number 6, right? Now we're going to use the dot product with different figures. Let's take I dot j. Well, the x and the y-axis are perpendicular, so that would give you 0, right? If we take j dot k, those are perpendicular, the y and the z-axis, so you would again get 0. Then say you've got k dot I. Again, all of this is perpendicular. You're going to get 0 every time. So you can't actually use the dot product in unit vector form with anything that's not in that unit vector's direction, because it's just going to end up going to 0. So we'll actually get some practice trying that out in a second. Okay, so that's how dot product with unit vectors is going to work. We're actually going to do that in a little bit to use the scalar product with vectors, because they are vectors, but you sometimes have them in vector component, right? Now, how and when is the dot product used? So here is an example, right? We've got a particle in the xy plane, undergoes displacement 2i plus 3j meters, while a constant force of 5i plus 2j newtons acts on the particle. So first, let's draw this. Right, so if we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so our displacement vector will go to here, right? That is our displacement vector. And then we have our force vector, which is going to come off over in this direction there. Okay, good. So is there more than one way to calculate work? Okay. Yes, there is. Now we can, let me show you the fast way, and then I'll show you the long way. Okay. So first, we're going to use the dot product, but we're actually going to do it in component form, right? So if we take S dot F, right? What we're doing is we're multiplying those vectors. So we're actually going to just take 2i plus 3j. We're going to multiply that by 5i plus 2j. We're just going to multiply these vectors. So to find that, right, that is going to give us, S dot F. That gives you work. Now here, to multiply these, we just FOIL, right? So 2i plus 5i is 10i squared. 2i plus 2j is 4. ij. Then we have 3j plus 5i. I'm sorry, 3j times 5i is 15ji. Then we have 3j times 2j, which is 6j squared. Now remember what we just talked about, though. When you take the unit vector I and unit vector j and dot product them or multiply them, you're going to get 0 because they are perpendicular. So here, this is perpendicular and this is perpendicular. So that actually goes to 0. We also said I squared and j squared, right, can be called 1, right? So that's actually not going to change the value at all. That's just going to kind of go away. So you've got 10 times 1 plus 6 times 1. This ends up being 10 plus 6 is 16 Newton meters. Okay. So that's how you can do this the fast way, because this is the fastest way to calculate work. Now, what we could do, okay, we've come down here. What you can do is find the magnitude of S, right, which we can do. We've got the vector, right? So you'd take S, I don't want that. Okay, S, okay, the magnitude would be the square root of 2 squared plus 3 squared, right? Magnitude of F would be 5 squared plus 2 squared, right? I'm just taking the Pythagorean theorem of their vectors, get those magnitudes. Then what you would have to do is find this theta. If you could find the theta between the two, then you could do f d cosine theta, or more accurately, f delta x cosine theta, right? So that is another way we could do it. However, it's really easy to just multiply your i's, multiply your j's, and then add them. It's pretty quick, right? So we've got 16 Newton meters of work done on that particle as it moves along that displacement vector under a constant force. Good. Now some dot product practice. Okay. So we've got vectors A and B. A is 2i plus 3j, and B is negative I plus 2j. So what we'll do first is we will sketch the vectors. Okay, we've got 1, 2, 3, 4, 5, 3, 4, 5, 1, 2, 3, 4, 5. So A is 2i plus 3j, so that will look like that. That is our A vector. Then B is negative I plus 2j, so that will come off in this direction. That is your B vector. Okay. Now we want to calculate the scalar product. What we could do, again, we could find the magnitude of each, then find this theta here. That is an accurate way to do it, that you're not wrong. However, it's a little bit more complicated and more time consuming. So first, let's calculate the scalar product. We take A dot B, okay, that would be 2i plus 3j times negative I plus 2j. And remember, if you multiply an I and a j, it's just going to be perpendicular and it goes to 0. So we take 2 times negative 1 is negative 2i squared. 3 times 2 is 6j squared. The j squareds and I squareds go away. You've got negative 2 plus 6 is 4 Newton meters. Real quick, right? Takes no time at all to do that. Actually, I guess I made the assumption that those are Newton meters, though. That is a unitless math equation, so the scalar product is just 4. Right? Now, if we want to actually find the angle between the vectors, this is the long process of doing it, right? But what we'll do is we will find the magnitude of each vector. Okay, so the magnitude of A is 2 squared plus 3 squared, all under the square root. Okay, so that would be, what, square root 13? 9, 4, yeah, square root 13. Magnitude of B square root of 1 squared plus 2 squared, you've got the square root of 5. Okay. Now, if you want to find the angle, right, what we can do first, we know the we know the scalar product. So we know that 4 equals AB cosine theta. We know what A and B are, so we could say 4 equals square root 13 times square root 5 cosine theta. So then theta would be the cosine inverse of 4 divided by square root 13 times square root 5. Okay, or you can do the trig up here. That would be more complicated. You would have to find this angle here, then subtract them from 180 to get the desired angle. Okay, or since we already know that theta is defined as the theta between A and B, you can use that right there, right? Not nearly as simple as doing the FOIL, though, right? To find the work. Easier way to find the angle, though, than doing the gold outline there, finding 2 different angles, then subtracting to find a third. All right, now calculate the dot product of the vectors shown down here in that video, in that image, to find work, and watch your units. Okay, this is going to be important. So here, right, we've got AB cosine theta. A and B can be arbitrarily defined. So let's just say A is 32 newtons. Is that 32.8 newtons? B, okay, 17.3 centimeters. Okay, we want that in meters, right? We could just call it Newton centimeters. That's fine. If we're wanting work, Newton meters is the best way to go. So we would say that's 0.173 meters. Okay. Now, what is the theta between them, though? So this is going to be tricky. We know that an entire circle, right, is 360 degrees. However, we are missing 90 degrees of it, right? This is 270 degrees. Now, what we will do is we will take out these angles here. So we take 270 minus 118 minus 132. Okay, so we've got 270 minus 118 minus 132. That should be 20. So this right here would be 20 degrees. Okay. So if we take 32.8 times 0.173 cosine of 20, okay, that will give us 5.33 Newton meters, or 5.33 joules. This could be an energy. I guess it does define work. Okay, so it does say it's work. So that is how we could find the work of just these 2 vectors here. Now remember, the key here is finding the angle. The magnitudes were given to you. Just change centimeters to meters. That's not difficult. But find that angle. The theta is special. The theta is the angle between those 2 vectors. Okay. Now let's talk about calculus meeting the dot product. Okay. First, it asks, what happens when force and displacement are lined up 90 degrees from each other? Okay, well, that means they're perpendicular, right? So that means that work would equal 0. Now, what is the technical calculus definition for work in this scenario? So work, okay, work is the integral of f of x dx from x naught to x final, right? Now, if you're looking at something perpendicular, though, that would be like saying work is the integral of f of x from x naught to x final dz. Say we want to integrate across the z-axis. Well, if we're going from x naught to x final on the z, or even better, we would say that this would be z naught from z naught to z final. for an f of x? Well, it doesn't go anywhere from z naught to z final because those are both 0. It doesn't exist on that axis. So this would be a big fat goose egg because there's nowhere for that integral to go. Right? Z naught and z final, it doesn't go anywhere. That function doesn't even exist in that axis. So it would just be 0. Now, if we look at this example, okay, a force F equals 6xi plus 5yj newtons. It acts on an object as it moves in the y direction from the origin to y equals 3 meters. Calculate the work done on the object by the force. So we want to take the integral from 0 to 3 dy. Well, if we did 6x dy, we're not really going to get anywhere because that part is only working in the I direction, right? That only works in the x direction. So we're not going to use that. We're just going to integrate 5y dy. So we will take 5y squared over 2 from 0 to 3. So you take your final minus your initial. You've got 5 times 3 squared over 2 minus 5 times 0 squared over 2. That all goes away. So we have 5 times 9 is 45 divided by 2. You get 22.5, and this is specifically Newton meters. Okay. So if we are only traveling in one direction, right, along one axis, you only need to worry about that part of the force because any force in the x direction cannot affect what's going on in the y direction, right, because it's perpendicular. Okay. Next, 2 more problems to work on if we have time. Well, it's a video, so we don't have to worry about class time. So first, as a pendulum swings back and forth, does the tension in the string do any work? And does the force of gravity do any work? So let's look at a pendulum swinging back and forth. I'm going to draw this down here. Okay. We've got a pendulum swinging an object. Let's say it's going this direction. Pendulum at the bottom, and then a pendulum almost reaching that apex there. Okay, so it asks, does the tension in the string do any work? Well, let's look. The tension, okay, is going to be along the string, right? Same here. Tension is along the string. Here, tension is along the string. Okay, so tension is a radial force, right? When we talk about pendulums, we revert back to not talking in x and y. We're going to start talking about radial and tangential direction because that's where our forces are going to orient. Now, let's look at whether the tension does any work. Well, our work, right, is we're going to go with FD cosine theta, right? That theta is the angle between the force and the displacement. Well, if our displacement is in this direction, they are at 90 degrees with each other, right? So they are perpendicular. Tension does no work. Work for tension equals 0 here. If we move to this example, they are also at 90 degrees. So work done by tension equals 0 again. And here, the work done by tension equals 0 because they are perpendicular, right? So the tension is doing no work as a pendulum swings back and forth. Now, it then asks, what about the gravity? So gravity is going to be a little bit more complex because the gravity is not simply perpendicular or parallel, right? The gravity is straight down at all times. So if we say that this is mg, right, and it has a radial component and it has a tangential component, right, and this would be our angle theta with relative to the vertical axis, right? So this mg cosine theta here, this tangent tangent component would be doing all of the work, right? So that is where we would be doing some work. So yes, mg is in the tangential direction. It would be doing work. Now let's look here. If we have mg going straight down, no, mg does not do any work, right? That is a right angle. So work of mg is 0 here. Here, we could say, I forgot to label this, work of mg, right? That is positive. We don't know the magnitude of it. We just know that it's positive, right? It is in the same direction as the displacement. That's what we know. Here, work done by gravity is 0. Now let's look here. If we have work done by gravity, let's look. We have it along the radial and along the tangential direction. Yes, it does look like we have work, right? We've got our little triangle there. Here, our mg does have a tangential component. However, displacement is this way. Mg is this way. So here, as the pendulum swings up, work of mg is negative, which makes sense, right? So if gravity is pulling a pendulum down as it swings, right, that's positive. But as it hits this middle point, goodness, as it hits this middle point here, right, that's positive, and now it's 0, and now it's negative as that pendulum swings up. Then when it hits its apex, the gravity will pull the pendulum along that displacement, and that will be a positive work. Then you hit 0, then you got negative, positive, 0, negative, positive, 0, negative. Okay, that's how gravity can actually do work on a pendulum. Okay? Great, good job. All right, so now a 300-gram object slides 80 centimeters along a horizontal tabletop. How much work is done in overcoming friction between the object and the table if the coefficient of friction is 0.2? And is that work positive or negative? So here is what we've got. Right? We've got a 300-gram or 0.3 kilogram object that slides 80 centimeters or 0.8 meters along a horizontal tabletop. I drew that horizontal tabletop with a zigzag because it's got friction. So how much work is done in overcoming friction between the object and the table if the coefficient of kinetic friction is 0.2? So if we look at this, we've got mu k is 0.2. Normal force would equal mg here. So we've got 0.3 times 9.81, which equals 2.943. So that newtons, right? 2.943, and we're going 0.8 meters. So if we want to know the work done to overcome that, right? We know that you must have at least more than the friction, right? If you're just balancing the friction, then you're not really doing, you're not going to cause any acceleration. So let's see, it's just sliding along the tabletop. We're just overcoming friction. We're not actually accelerating, which means that we just have to match it. So we take the force, right? The friction force would be 0.2 for our mu times normal force, which is 2.943, which is 0.5886 newtons. Okay, so if we are overcoming that, the work that overcomes this would be the force, 0.5886, times the displacement, 0.8. And friction always acts opposite of motion, right? So the force overcoming it is going to be parallel, right? We're assuming, right? It actually doesn't even ask about the force. It just says how much work is done. So we don't know what all is going on, but the work to overcome this friction is 0.47 Newton meters. That is the work it takes to just balance that friction to allow it to slide, right? Good. And remember, that's just allowing it to slide. That doesn't mean that it's accelerating. That just means that we're matching the friction to allow it to move. Good. So that is what we have for our work methods 2 video over the dot product. Okay, next we're going to go on to scales, not scales. We're going to go on to springs and talk about how work and force of springs in general is very different from everything else we've done before.